Welcome to the video lecture series of electronic devices. This is lecture number 23 and today I am going to discuss some numericals based on carrier concentrations. You must have studied about the carrier concentrations, how to calculate the concentration of electrons, holes, what is Fermi direct distribution. In case you have missed it, then you can see the previous video lectures. Let us begin today's lecture. First question is, in n-type semiconductor, the Fermi level is 0.3 electron volt below the conduction band. Determine the electron and hole concentration in sample at room temperature, which is 300 Kelvin, given that Eg is 1.1 electron volt, Ni 1.5 into 10 raised to the power 10, and the value of K is given in electron volt per Kelvin. Let us solve this. In intrinsic, Fermi level is located approximately at the center of band gap. This you know that. So, in case of intrinsic semiconductor, what would be EC minus EI? If you calculate this, it would be what? This would be in the middle of the band gap, means that is Eg upon 2, and the value of Eg is given 1.1 divided by 2. So you will be getting this is as 0.55 electron volt, and this is for silicon, means for pure semiconductor. And here in this question it is given that in n-type semiconductor, in case of n-type semiconductor, the Fermi level is 0.3 electron volt below the conduction band. It means EC minus EF is what? 0.3 electron volt. And at the same time, you know how to calculate the electron concentration. The electron concentration is denoted by N0. Let me write the formula. Electron concentration, you can write it as N0 is what? Ni e raised to the power Ef minus Ei upon K into T. So here what is our requirement? Our requirement is to put these particular values and calculate the value of N0. But here you can see there is a term Ef minus Ei. How to calculate it? You need to calculate Ef minus Ei, but you already know Ec minus Ei. If you subtract Ec minus Ef from Ec minus Ei, what you will be getting over here? You will be able to calculate Ef minus Ei, and this term, this is what? This is 0.55 minus 0.3. It means what is the value of Ef minus Ei? 0.25 electron volt. Now let us substitute the values in the given equation. Means what is N0? Ni is being given 1.5 into 10 raised to the power 10 exponential Ef minus Ei you have already calculated, which is 0.25 upon the value of K is 8.62 into 10 raised to the power minus 5 into T is 100, 300. Now simplify this particular value. You will be getting this is 1.5 into 10 raised to the power 10. If you simplify this exponential term, it would be 1.58 into 10 raised to the power 4, which will be coming out as 2.37 into 10 raised to the power 4 centimeter cube by centimeter cube. So you have calculated N naught. Now what is your requirement? You have to calculate the whole concentration. So you know the formula N naught P naught is equal to what? Ni square. So from here what would be P naught? It would be Ni square upon N naught. Just substitute all these values. Ni is being given, which is 1.5 into 10 raised to the power 10. Its square upon N naught you have calculated, which is 2.37 into 10 raised to the power 4. Just simplify it, and after simplification you will be getting its value as 9.5 into 10 raised to the power 5 per centimeter cube. So this is how you can calculate the value which is related to the electron concentration, that is N naught, and hole concentration, which is P naught. I hope now you can solve this question. Question number 2 is, in N-type semiconductor the Fermi level lies 0.3 electron volt below the conduction band at room temperature. Now if the temperature is increased at 330 Kelvin, what is the new position of Fermi level? So here you have to derive by varying temperature the Fermi level varies, but what is its position? Let us solve it. We know that what is N naught? N naught you can write it as N of C 1 upon 1 plus exponential EC minus EF upon KT. This is how you can write down the formula. So N naught can be approximated as NC upon exponential EC minus EF upon KT, because this term is quite high in comparison to 1. From here you can write down as, let me write down it as NC upon N naught would be what? Exponential EC minus EF upon KT. Just you have manipulated the terms. So if you have to simplify further, you have to take ln log base E, which is of NC upon N naught. So this you could write it as EC minus EF upon KT. So from here let us more simplify and write down it in terms of EC minus EF. What would be it? EC minus EF would be KT times ln NC upon N naught, and now you can utilize it while solving the question. So here it is given that two conditions at room temperature, means at 300 Kelvin, substitute the value in the Question number 1, here it is being given that the Fermi level lies 0.3 electron volt. So what it would be? 0.3 electron volt, which is equal to K, and temperature is 300. Then Ln Nc upon N naught. Let us write it as equation number 2. Now the second case, at temperature T is equal to 330 Kelvin. Now equation 1 will be, this is EC minus EF, which is equal to K, temperature is 330, Ln Nc upon N naught, and let us say this is equation number 3. Now divide equation 3 by equation 2. To simplify it, let us divide equation 3 by equation 2. So what you will get over here? This term would be EC minus EF upon left hand term of equation 2 is 0.3. Right hand side would be 330 upon 300. Rest of the terms will be cancel out. It means EC minus EF will be what? This is 0.33 electron volt. What does it means? It means Fermi level will lie 0.33 electron volt below the conduction band. So this is the answer. Question number 3 is, determine the thermal equilibrium hole concentration in silicon at 400 Kelvin, given that the Fermi energy is 0.27 electron volt above the valence band energy, and the value of Nv for silicon at 300 Kelvin is also given. Let us solve. So now you have to calculate, since the value of Nv is given at 300 Kelvin, now you have to calculate the value of Nv for silicon at 400 Kelvin. So this value will be, this is what? 1.04 into 10 raised to the power 19 into 400 upon 300, its square root. Simplify this term, you would be getting it as 1.6 into 10 raised to the power 19 per centimeter cube. And at the same time, you must know that hole concentration is given by, how to write down this particular formula? This is what? P naught is equal to Nv e raised to the power Ev minus Ef upon Kt. Now substitute all values over here. See, what is Nv now? Nv for 400 Kelvin, this is 1.6 into 10 raised to the power 19. This term exponential. This is what you can write as minus Ef minus Ev upon K into T, and this value Ef minus Ev is being given, which is 0.27. So this equation would be 1.6 into 10 raised to the power 19 exponential of minus 0.27 upon Kt. See, these particular terms is in the electron volt. The value of K, you know, it is 1.38 into 10 raised to the power minus 23. T is what? T is 400 Kelvin. Multiply it and then convert it into the electron volt. You must remember 1 electron volt is equal to what? 1.6 into 10 raised to the power minus 19 joule. So if you convert the value of K into V into electron volt, then this value will be 0.0345. Now simplify this term and this particular value will be coming out as 6.43 into 10 raised to the power 15 per centimeter cube, which is the thermal equilibrium hole concentration. This is the final answer. Moving ahead, question number 4 is, here silicon sample is doped with 10 raised to the power 17 AS atoms, arsenic atoms. Determine the equilibrium concentration of holes at 300 Kelvin. Ni is given, and here you have to also find out the relationship of EF with EI. How to solve this particular question? See, in this case, what is being given? Sample is doped with arsenic atoms. This is a kind of donor atom. Donor atom. So here concentration of this donor atoms will be very high in comparison to Ni. At the same time, we can assume N naught electron concentration is almost equal to the donor one, and you know one of the formula N naught P naught is equal to Ni square. In solving these numerical questions, the important thing is you must remember all these formulas. So from here you can calculate the value of P naught. P naught will be what? Ni square upon N naught. Ni square is being given, which is 1.5 into 10 raised to the power 10, its whole square, and N naught is given, for which we have assumed it is equal to Nd. So this particular value will be what? 10 raised to the power 17, and if you simplify it, you will be getting it as 2.25 into 10 raised to the power 3 per centimeter cube. Now you have to calculate the equilibrium concentration of holes. So you have already calculated equilibrium concentration of holes. Next, you have to determine the relationship between EF and EI. So now let us write N is equal to Ni exponential EF minus EI upon KT. This particular term you are already aware. How to write it down over here? If we talk about the carrier concentration, so from this particular equation you can write EF minus EI would be what? KT times, if you take ln, so this is N naught upon Ni. K and T, you have to write it down into the electron volt. K Boltzmann constant and T is being given, which is 300 Kelvin. Multiply it and then convert it into the electron volt. It would be 0.0259 ln N naught, which is 10 raised to the power 17, and Ni, which is 1.5 into 10 raised to the power 10. Now simplify it. Upon simplifying this particular value, you will be getting at 0.407 electron volt. You must check your answers. All the values are in the electron volt. So here what is EF minus EI you have calculated? This is 0.407 electron volt. You must remember this value of KT is in electron volt. You have multiplied and then converted it. So what you can conclude over here? Here, find relationship between EF and EI. It means the difference between EF minus EI is 0.407. So if you plot the band structure, you can see if this is the energy band for valence band, this is the energy band for conduction band. So you can draw over here. This value of EI, this particular level will be somewhat in the middle, and EF will be nearby this point, and this particular difference, this would be what? 0.407 electron volt. So this is how you can explain it over here. Moving ahead, next question is, determine the probability that a state in the conduction band is occupied by an electron. Also calculate the thermal equilibrium electron concentration in silicon at 300 Kelvin. Assume Fermi energy is this, which is below the conduction band. The value of Nc for silicon at 300 Kelvin is also being given. It means here you have to calculate Fe and N naught. Let us solve. What you need to calculate? You have to calculate Fe and N naught, these two values. Given terms you must note over here. Given terms is what? Ec minus Ef, which is 0.25 electron volt. N of C is 2.8 into 10 raised to the power 19 per centimeter cube. K you already know, which is the Boltz's constant, 1.38 10 raised to the power minus 23. Temperature is given 300 Kelvin, and the value of KT in electron volt 0.0259. Multiply K into T, convert it into the electron volt. 1 electron volt is equal to 1.6 into 10 raised to the power minus 19 joule. So accordingly you can convert it over here. Now first thing which you have to calculate, F of E. Let us write the formula. This is what? 1 upon 1 plus exponential EC minus EF upon KT. And in this denominator term you can see the value of this term will be quite high in comparison to 1. So it can be ignored, and at the same time you can simplify it and you can write it as a exponential. This would be minus EC minus EF upon K into T. Now just substitute all these values because you know you have already calculated. So what is this particular term? This is e raised to the power minus of 0.25, and the value of KT in electron volt 0.259. Just simplify it and you will be getting the value of Fe as 6.5 43 into 10 raised to the power minus 5. So this must be the answer for the first case. Now let us solve the second one, where you have to calculate the thermal equilibrium electron concentration, means N naught. And the formula of N naught is what? N of C e raised to the power minus EC minus EF upon K into T. Again substitute the value. NC is 2.8 into 10 raised to the power 19 e raised to the power minus 0.25 upon 0.0259. Simplify it. You will be getting the value of N naught as 17.97 into 10 raised to the power 14 per centimeter cube. So one thing you have to calculate Fe, you have already calculated, and second N naught. Clear? Next and last question. Here you have to determine the effective density of state function in conduction band for a semiconductor in which effective mass of electron is 1.5 m naught. How to solve this? Effective density of state function, you must be aware about this formula. Effective density of state function in conduction band. This particular formula will be what? This is NC is equal to 2 times 2 pi effective mass of electron K into T upon H square, and this is 3 by 2. Now substitute all these values. Here it is being given that effective mass, this is what? 1.5 times m naught, and m naught you already know. M naught value is 9.1 into 10 raised to the power minus 31. So this one term you already aware, and the temperature which is being given 300 Kelvin. Value of K is Boltzmann constant 1.38 into 10 raised to the power minus 23. And what is the value of H? H value you are already aware, just you have to remember it. It's 6.63 into 10 raised to the power minus 34. Now substitute all these values in equation 1. Substitute all values in equation 1. You will be getting the value of NC. This is what? 2 into 2.2 into 3.14, which is pi, into K, which is 1.38 into 10 raised to the power minus 23. T is 300. So this is the term for the numerator. Denominator is 6.63 into 10 raised to the power minus 34. It's square, and just you have to simplify it. This would be your final answer. So I hope all the questions are clear to you, but the only thing you have to remember the formulas. Thank you so much for watching today's lecture.